find the limit of an if exists. So for each of this sequence, we are asked to find the limit. So let's see the first part, the A part. In A, the limit is, the sequence is an is equals to 1 plus 3 over n the power of n. So the question is the limit of this sequence 1 plus 3 over n the power of n as n approaches to infinity. So let's see what the limit looks like for this part. So there is one thing that we know from the limit of the form. The limit of 1 plus 1 over x the power of x as x approaches to infinity is e. You know this thing from your grade 12 lesson. So we will apply this concept. So now we have to convert this sequence in this form. So let 3 over n is some number 1 over x. Here this tells us n becomes 3 times x. Okay, so as n approaches to infinity, obviously this x also will go to infinity. So now the limit of 1 plus 3 over n the power of n as n approaches to infinity is the same as the limit of 1 plus 1 over x the power of in place of n we can substitute 3x as x approaches to infinity. So this can be written as the limit of 1 plus 1 over x the whole x, okay, as x approaches to the whole x as x approaches to infinity. So this is exactly A according to this definition. So this result becomes e cubed. Okay, so the limit of 1 plus 3 over n the whole n as n approaches to infinity is e cubed. Now let's see the B part. In B we have a sequence. an is equals to cubed root of n plus 2 minus cubed root of n plus 1. Okay, so we will evaluate the limit of this sequence an as n approaches to infinity. So to evaluate this limit, we need to write this radicals in some other form by rationalizing. So this cubed root of n plus 2 minus cubed root of n plus 1 can be rationalized by some rationalizing factor. So the rationalizing factor here will be, let me use different color. It will be cubed root of n plus 2 the whole square plus cubed root of n plus 2 times n plus 1 plus cubed root of n plus 1 the whole square. Okay, we multiply this over cubed root of n plus 2 the whole square plus cubed root of n plus 2 times n plus 1 plus cubed root of n plus 1 the whole square. Okay, this is the rationalizing factor for the given cubed root. ለዚህ cubed root rationalizing factor እዚህ በቀይ የጻፍኩትን ይመስላል። ይሄን rationalizing factor ካላወቀን ይሄን ጥያቄ ምንሰራበት ሌላ ኦፕሽን ያለ አይመስለኝም። So we need to have this rationalizing factor. Now this rationalization gives us 1 over cubed root of n plus 2 the whole square plus cubed root of n plus 2 times n plus 1 plus cubed root of n plus 1 the whole square. Okay, this is the rationalization form of the given radicals. Yes, the rationalization ይሄንን ይሰጠናል. Therefore the limit of cubed root of n plus 2 minus cubed root of n plus 1 as n approaches to infinity is the same as the limit of 1 over cubed root of n plus 2 the whole square plus cubed root of n plus 2 times n plus 1 plus cubed root of n plus 1 the whole square as n approaches to infinity. Now, obviously, the limit as n approaches to infinity, 1 over very big number will be 0. Okay, therefore, the limit of the given sequence will be 0. Therefore, you can say the limit of an as n approaches to infinity ምን ይሆናል ማለት ነው? 0 ይሆናል ማለት ነው ለዚህ sequence. Okay, in C we have the sequence in C is n square minus 1 over n the whole n. Okay, we need to rewrite this sequence first in different forms. ይህንን sequence በተለያየ መልክ መጻፍ እንችላለን. One of the different ways of writing this is here ይህንን ማንኛውም number a እንዴት ተብሎ ሊጻፍ ይችላል? e the power of logarithm of a in base e ብለን መጻፍ እንችላለን. This is one of the property of logarithm. So this sequence can be written as e the power of logarithm of base e here n square minus 1 over n the whole n ማድረግ እንችላለን. Still this can be written as ይሄ እንዴት ሊጻፍ ይችላል? e the power of n times ln of n square minus 1 over n ብለን መጻፍ እንችላለን. So የሎጋሪዝም ፕሮፐርቲ እንጠቀማለን ማለት ነው. So the limit of an as n approaches to infinity is the same as the limit of e the power of n ln of n square minus 1 over n as n approaches to infinity. So የዚህን ሊሚት ኢቫሉዌት ለማድረግ በሰብስቲቱሽን የዚህን ሊሚት ማወቅ ይጠበቅብናል. So we need to know the limit of n times ln of n square minus 1 over n as n approaches to infinity. Okay, so we need to know this thing. So this is again the same as the limit of ln of n square minus 1 over n the whole 1 over n as n approaches to infinity ማለት እንችላለን. Okay, so የዚህን ሊሚት ኢቫሉዌት አድርገን ወደ ነበርንበት ወደዚህ እንመጣለን ማለት ነው. So if we evaluate the limit of this sequence, we will get infinite over 0, okay, which is indeterminate form ይባላል. ይሄ infinite over 0 ስለሚሰጠን we use L'Hopital rules to find the limit. So ምን ይሆናል ማለት ነው? L'Hopital rules ስንጠቀም the limit of ln of n square minus 1 over n derivative over 1 over n derivative as n approaches to infinity ይሆናል ማለት ነው. So ይሄን derivative ሰርተን ln እና 1 over n derivative ሰርተን simplify ስናደርግ የምናገኘው the limit of minus n cube minus n over n square minus 1 as n approaches to infinity. So this result is negative infinity, as you can check. So የዚህ result negative infinity ከሆነ እንመጣለን ወደዚህ ጋር እዚህ ኦሪጂናል እንትን ውስጥ ስናስገባ ምንድነው የሚሆነው? e is a power of negative infinity, which is the same as 1 over e is a power of very big number. So ይሄ ምንድነው የሚሆነው ማለት ነው? 0 ነው የሚሆነው ማለት ነው። Therefore the limit of n square minus 1 over n, the whole n, as n approaches to infinity, will be 0. So የዚህን ሊሚት ለመመለስ ይሄንን ኤክስፕሬሽን በሎጋሪዝሚክ ፎርም መቀየር ግድ ይላል ማለት ነው። Let's see the d part. ወደ d part እንመጣለን። In d we have d ጋር ስንመጣ the sequence is an is equals to n over n plus 1 times sine of n pi over 2. To determine the limit of this sequence, we need to observe some of the patterns of the sequence. So what's the first term? The first term in this sequence is put n is equals to 1. n and 1 are 1 over 2 times sine of pi over 2 ነው የሚሆነው። So the first term is 1 over 2. ምክንያቱም sin pi over 2 ማለት sin 90 ነው። result 1 ነው የሚሆነው። a2 or the second term is 2 over 3 በn ቦታ 2 እያስገባን እንሂድ። Okay, 2 over 3 times sine of 2 by 2 ስለሚጣፋ sin pi ይሆናል። sin pi ደግሞ 0 ነው የሚሆነው። Okay, so 2 over 3 times 0 is 0. The third term is 3 over 4 times sine 3 pi over 4 ነው የሚሆነው። Sine 3 pi over 4 is negative 1, so the result is negative 3 over 4. The fourth term is 4 over 5 times sine 2 pi. Okay, በn ቦታ 4 እናስገባለን። sine 2 pi is 0. 4 over 5 times 0 is 0. Similarly, the fifth term is 5 over 6 times sine 5 pi over 2, which is 5 over 6 itself. Okay, ይሄ 1 ስለሆነ እያለ ይቀጥላል። From this you can also observe that the sixth term will be 0. So here ምን observe እናደርጋለን ማለት ነው? an will be 0 for n even ሲሆን any terms 0 ነው የሚሆነው. For other values an will be some number. Okay, an will be some number. An may be approaching 1 or minus 1 as n approaches to very big odd number, right? እነዚህ ቁጥሮች 1 over 2 5 over 6 ወይ ፖዚቲቭ 1 ነው ወይ ኔጌቲቭ 1 ሊሆን ነው የሚቃረበው። So the limit is not unique. Okay, so as n approaches to infinity, the value of the nth term will go to 0 or 1 or minus 1. There is no unique number for the nth term. So ምን እንላለን ማለት ነው? The limit of the sequence an as n approaches to infinity doesn't exist. So the sequence doesn't exist. The limit of the sequence doesn't exist. Now let's see the e part. The e part, in e the sequence an is tan hyperbolic n. Okay, tan hyperbolic n is the same as sine hyperbolic n over cos hyperbolic n. Okay, hyperbolic function ምን ማለት እንደሆነ ካላወቃችሁ ሳይን ሃይፐርቦሊክ ዲፋይን የሚደረገው በዚህ ፎርሙላ ነው። e is a power of n minus e is a power of minus n over 2. This is the formula for sine hyperbolic over cos hyperbolic ደግሞ e is a power of n plus e is a power of minus n over 2 ይሆናል ማለት ነው። So this is the same as e the power of n minus e is the power of minus n over e the power of n plus e to the power of minus n ይሆናል። this is tan hyperbolic n. okay, so ይሄንን simplify ስናደርግ this is the same as e to the power of 2n minus 1 over e to the power of 2n plus 1 ይሆናል ማለት ነው። so our sequence an or tan hyperbolic n is the same as e to the power of 2n minus 1 over e to the power of 2n plus 1 ይሆናል ማለት ነው። so let's see the limit of an as n approaches to infinity, or the limit of tan hyperbolic is e to the power of 2n minus 1 over e to the power of 2n plus 1 as n approaches to infinity. If you take big number for n, this becomes infinite over infinite. So it requires L'Hopital rule. So using L'Hopital rule, we can say that the limit is the same as e to the power of 2n minus 1 derivative over e to the power of 2n plus 1 derivative as n approaches to infinity. So this is the same as the limit of 2 times e to the power of 2n over 2 times e to the power of 2n as n approaches to infinity. So እዚህ ጋር የሚጣፋ ነገር ይኖረናል፣ ይሄን በዚህ ይጣፋል። so it becomes 1. so the limit of 1 as n approaches to infinity is 1 itself. Therefore the limit of tan hyperbolic n as n approaches to infinity is 1. The f part, in f the sequence an is n square times n factorial over n plus 2 factorial. ይሄንን simplify ማድረግ ይጠበቅብናል በመጀመሪያ። so this is the same as n square times n factorial over n plus 2 factorial ማለት n plus 2 times n plus 1 times n factorial ማለት ነው። ኦኬ አንድ ነገር ላስታውሳችሁ 10 ፋክቶሪያል ማለት 10 times 9 times 8 እያለ እስከ 1 ይሄዳል። so 8 ፋክቶሪያል ብላችሁ መቆም ትችላላችሁ። ስትፈልጉ 10 times 9 ፋክቶሪያል ማለት ትችላላችሁ። it's the same. so n plus 2 ፋክቶሪያልን እንደዚህ ማስቀመጥ ከቻልኩኝ አሁን n ፋክቶሪያል በn ፋክቶሪያል ጣፋል። so ምን ይሆናል ማለት ነው n square over n plus 2 times n plus 1 ይኖረናል ማለት ነው። so our sequence an becomes n square over ይሄን ስታበዙት የምታገኙት n square plus 3n plus 2 ነው የሚሆነው። so now we can calculate the limit of this sequence. so the limit of n square over n square plus 3n plus 2 as n approaches to infinity ምንድነው የሚሆነው ማለት ነው 1 ነው የሚሆነው። you can check that this is the same as the limit of n square over n square over n square plus 3n plus 2 over n square. okay እንዲህ አርገን ብንጽፈው ይሄ ምንድነው የሚሆነው the limit of 1 over 1 plus 3 over n plus 2 over n square as n approaches to infinity. so now here as n becomes infinity, this term becomes 0, this term becomes 0. so 1 plus 0 is 1. 1 over 1 ምንድነው የሚሆነው 1 ነው የሚሆነው ማለት ነው። okay so the limit of n square times n factorial over n plus 2 factorial will be 1.